Hello everyone, welcome to Sergio Prado's YouTube channel. Um, so I've been doing lots of talks lately, and you can watch all of those talks in this YouTube channel. And this year, 2024, I decided to start recording a few kind of quick, small videos, like tutorials. Um, I have a blog, and usually I write there about different topics on embedded Linux, security, embedded development in general. And for some of my videos, for some of my articles, I will probably record a quick video to show you because some people like to read and some people like to watch. So I hope you enjoy this video. And if you really do, leave a comment in the video and let me know if you like it and if you want more of this kind of content. So let's go directly to the topic. Um, I want to show you today how to debug the Linux kernel with GDB. So GDB is a very powerful tool. You can do a lot of different things in terms of debugging with GDB. But at the same time, it's not a tool for every kind of bug that you're going to face. I mean, usually when I teach um, debugging, I usually say that there are different techniques and tools, and depending on the situation, um, you're going to have to use one of them or maybe mix a few of them, right? You can debug software by adding prints in the code or tracing the code. You can debug the software interactively, like with GDB. Um, you can use tools to help you debugging the software, right? I usually call those tools debugging frameworks. Um, and You can do crash dump analysis, like if you have logs of a crash, you can do what we usually call post-mortem analysis. So again, there are different tools and techniques, and depending on what kind of problem you have, you're gonna have to identify the best tool technique. And GDB is one of them. Usually when the problem is more complicated, when you have to inspect memory, maybe look at the backtrace, the call stack, GDB might be a good solution. Um, One problem with GDB is that it's an instrumentation tool. It might impact the execution of the system. Sometimes it's complicated to create an infrastructure to debug with GDB, so you might have to take all of this in consideration if you decide to use GDB. And as you're gonna see here, you can use GDB in the Linux kernel. Um, so one thing that we might think about is how, right? Because how can we debug a software? Like we want to debug the kernel, but for that we need an infrastructure in the kernel to debug itself, right? Of course, that can be done with external hardware support. So, for example, you could debug the kernel with GDB using a JTAG interface. But that's not what I'm talking about here. JTAG it's more complicated to use. Usually is required, especially if you are doing board bring up. If you want to like debug the bootloader, for example, you're gonna need GDB. You're gonna need a JTAG interface for that. If you want to debug the early startup of the Linux kernel, you might need JTAG for that. But as soon as the kernel is booting, you don't need uh, JTAG for that anymore. And if you want to debug the kernel step by step and inspect the memory, then you can do that with GDB. How can you do that? You can do that works because the Linux kernel has an implementation of the GDB server protocol. So inside the Linux kernel, we have this implementation that is usually called KGDB. And if you enable it and properly configure the kernel, you can use GDB to debug the kernel. And that's what I want to show you here in this quick video. So before talking about the process, I want to show you my environment. So first of all, I'm using the BeaglePlay development board. As you can see here from this video here, this is the board. I'm pointing to another camera. BeaglePlay is a very, very nice development board. I'm really enjoying work with BeaglePlay. It's really open source hardware. Lots of hardware interfaces. It has mainline support, kernel mainline support. That for me it's very important because I'm usually working with the latest kernel features, and having mainline support is usually much better. Um, Now I have the BeaglePlay connected to my development machine. So over a serial port, as you can see here, the serial port cable. This is the power cable here, and also I have the Ethernet cable. Um, for the serial connection, so that's one important thing. If you want to debug with GDB, you're going to have to select one communication interface. That could be serial or network. But for network, like the Linux mainline kernel doesn't have the drivers to for KGDB over network. You would need to apply this uh, externally. There are a group of patches that you need to apply. That's not what we are going to do here. So here we're going to use the serial port. And I would recommend the serial port. I think it's more stable than doing over the network. For user space application, using the network is much better because it's faster. But for kernel debugging, I usually use a serial port for that. And the only problem that I have here is that I just have access to one serial port. Of course, the BeaglePlay has other serial ports, but I'm not going to use it. So I want to share the serial port between the console. I want to have access to the console. At the same time, I want to use this serial port interface for debugging. So what I'm using here, I'm going to show you how it works. So I'm going to use what's called an agent proxy for the serial port. This is a project provided by the kernel community. And everything that I'm talking about here, it's written in my blog post. I'm gonna leave the link in the description of the video if you want to read it. Um, so in the end of the article, I talk about this agent proxy that makes it possible to share the serial port between the console and also the debugger. So this is the link for the agent proxy. It's a project that is hosted in the kernel website. You can just clone it and then build it. And the way it works is that you just run the proxy with the serial port that is connected to the board and the baud rate. Then this program will create two pseudo terminals for you, as you can see here. It's 18 and 24. So 18 is for the terminal emulator for the console, and the 24 is for GDB. So now I can start my serial program here using this pseudo TTY. I'm gonna use minicon for that. So as you can see, I already have access to the system. in the serial port. This is the console. I can just quickly reboot it to show you the complete boot process. Um, and then the other part I'm gonna use for debugging in a few minutes. So that's the first thing here. I'm sharing the serial port for debugging and console. That's why I'm using this agent proxy. If you are not sharing it, so there is no need to use this proxy. Just to make sure. Um, now to the system. So here I'm running the latest kernel. Um, Actually, one of the latest. It's been a few days that I didn't pull from mainline, but I'm running a mainline kernel here. Can show you here 6.7 something. And let me explain you how my infrastructure looks like. So I'm booting everything from the network. I have in my development machine, I have a TFTP server, and I'm hosting the kernel and the device tree files there in the TFTP server. And then the bootloader is loading those files over the network. So the board is connected to my machine. And let me reboot again and stopping the bootloader. So this is U-boot prompt. And then here we can see, let's inspect a few variables. So here you can see that my boot semid command, that's the command that will boot the system. Here I'm loading the kernel using TFTP and also loading the device tree over TFTP. If I run boot here, we're going to see those hashtags. That means I'm booting over the network. So I booted the kernel with a device tree over the network. That is very nice because it's easy to update. So as soon as I compile the kernel, I can just copy to my TFTP directory and boot over the network. Just reboot the system is enough to test a new kernel image. Now for the file system, I built one with build root, a very small file system. So I built a file system for ARM64 with build root, and then I'm booting over the network as well. So I uncompressed the file system here. So this is the root file system, and then I have a NFS server in my machine sharing this directory. In the device, I'm passing a few parameters to the Linux kernel to boot over the network. This is the complete command line parameters. As you can see here, root equals dev NFS, and then the NFS parameters, so I'm booting over the network. This is the perfect, I would say, architecture for development on embedded Linux, because almost everything is on the network, is on my machine. Only the bootloader is flashed in the device. All right, but that's not the focus on this video. I just wanted to show you my infrastructure, right? Let's talk about debugging with GDB. So to debug with GDB, there are 3 steps. First thing that you have to do is to compile the kernel with GDB support. That's the first thing that you have to do. And that is basically one option that you have to enable, but you might want to check a few extra options. Let me quickly show you. So I have here the kernel source code. I already compiled it because I didn't want to wait here in the video for the kernel to be compiled, but I'm gonna do quick changes. So I'm opening the kernel menu configuration interface, and I'm gonna show you a few options. So the first one is config kgdb. That's the one that you really should enable. Then I can just search for it here, kgdb. It is already enabled, as you can see here, right? It has yes, it's this option here. It is already enabled. And as soon as you enable, you would probably want to enter into the menu and see if the KGDB over the serial console is also enabled. Those are the two important options um, that I'm showing here, right? Usually when you enable KGDB, this option here is also enabled. This is important to get the kernel into debug mode, as we're gonna see. Um, Another option that is important to make sure it is enabled is this one, config debug info. Because when debugging the kernel, you're gonna probably need in your host machine the kernel image with debugging symbols. And debug info, that's the purpose of this option. Uh, this is basically here in kernel hacking. Compile time checks and compiler options. Um, Now, one thing that you need to make sure that it is disabled is this one, config debug info reduced. That's this option here, right? Config debug info reduced. Usually it is enabled, but if you really want a better experience debugging with GDB, I would recommend disabling it. What else? There is this other option. So the kernel has a feature to randomize the address space layout. So every time it boots, it will use a different address. That might impact the debugging experience as well. So you might want to disable that. Not sure if mine is disabled. Possibly yes, I disable it as you can see. Uh, you might want to disable this at the kernel configuration during build time or also at runtime. At runtime, you can just pass a kernel parameter. That's this one, no KASLR. So if you pass this option, the kernel will boot without this feature enabled. So those are a few like options that you might want to check to have debugging support in the kernel. Um, I'm gonna just quickly change one thing so I can like rebuild the kernel. I'm gonna change the local version. So I'm gonna add here dash YouTube. So we can check that we are running this kernel, right? Then I'm gonna, now the build should be faster. Just restarted config and let me confirm here. The build should be faster because almost everything is already built. Just change it, the kernel local version. This will be appended to the kernel version. So we should just regenerate the image. So it should be fast. And the nice thing about using TFTP for booting is that I can just now copy the new image to my TFTP directory, and then I can just reboot the device, and the new kernel will boot. Let's see. So with this, we have now support in the kernel for debugging with KGDB. Let's just check the version. As you can see here, we have dash YouTube that I just added, just to make sure that we are running the correct kernel image. Now, the next step is to get the kernel into debugging mode. So there are two ways to do this. You can do this at boot time or at runtime. at boot time, you would pass to the kernel some parameters, like this one. You will need to pass this KGDB OC parameter with the serial port that you want to use for the communication, and also KGDB wait to tell the kernel, please wait and don't boot, wait for a connection from GDB. This is useful if you want to debug the boot process, the kernel booting process. So here I'm going to do something different. I want to debug the kernel at runtime. So I want the kernel to get into debug mode at runtime. So for that, I can run two commands in the terminal. The first is this one. So here I'm just configuring the serial port that I want to use for debugging. You can see in the kernel logs a message that the serial port was registered as an interface for KGDB. And now we can get the kernel into debugging mode. So here we are using a feature from the kernel called magic CSRQ. And basically you can just send commands to the kernel over this interface. Here we are using this G command that gets the kernel to debug mode. So now the kernel, as you can see from these messages from the kernel logs, the kernel is in debug mode. I cannot do anything, like everything is freezed. The kernel is waiting for the connection from GDB. Now it's time to go to the host machine and connect to the Linux kernel. So for that, we want to use the debugger from your toolchain, right? So this is my toolchain. And you should pass to it the kernel image with debugging symbols. When you build a kernel, this VM Linux image will be generated. So this is a special image. This is not the image that you use to boot the kernel. It's the image kernel, it's the kernel image in the ELF format. One of the purposes of this image is to debug the kernel. As you can see here, it's an ELF image. So you can open it with GDB. Another option that I want to pass here is -TUI. So this option will open GDB in a kind of more, let's say, graphical interface, right? You can really see the source code here, because by default GDB provides a command line interface. And if you want a better experience when you are like running the code step by step, then the TUI mode is really helpful. So in this TUI mode, you're gonna see a few windows, right? Here by default, you can see two windows. On the top, you have the source code. In the bottom, you have the command line interface. You can open more windows if you want, like if you want to see the registers from the CPU, you can also open. But let's stick with these two windows. Now, what I want to do is to connect to the Linux kernel. So the command from GDB is target remote and then the serial port. Let's just check what is the serial port. As you can see, this other one, right? The first one we are using in the console. This second one is the one that we want to use in the GDB command line interface. So target remote and the serial port. Here we go. Now we are connected to the kernel and ready to debug the kernel. The kernel is still stopped, right? It is not running, as you can see here in the console. Let's do a quick test. So I'm gonna add a breakpoint to a function. I always forget the name, GPIO. Sorry. GPIO keys, GPIO report event. So I'm adding a breakpoint to this function. This is the function that is called um, when you have events from uh, GPIO connected buttons or in kind of input device connected to a GPIO. I'm doing this because there is a button in the Beagle Play Debug board. So as soon as I push this button, then the kernel will stop the execution in this breakpoint. So I added the breakpoint. You can just confirm that here. It is there. Then I'm going to continue the execution of the kernel. So now the kernel should be running. If I go to the console, the kernel is running. So everything is working as it should be, right? And then as soon as the kernel gets into that breakpoint, the execution will stop. So I'm going to press the button and see how it goes, right? Here we go. Now we are in the kernel function, and then we can do step-by-step code execution, like you can do next, next, next. I can print, like inspect the memory, right? So let's see what we have inside this structure, b data. So you can inspect the structure. I mean, you can do a backtrace. You can see like all of the call stack for this function. Then you can see there that is actually this function is being called from the interrupt context, as you can see here. Generic handle IRQ desk. That's very interesting. You can really put breakpoints anywhere, almost anywhere, let's say. Very nice. As soon, I mean, now I can just run, type continue if I want to continue the execution. It stopped again because there are two events, the pressed and the released event. So continue again. Now the kernel is running again, and then I can. So you can really debug the kernel with GDB, and that's how it works. Before you go, I want to show you another thing. You can do the same thing with graphical environment if you want. So let's say you like, let me stop here. Let's say you like graphical development environment, right? And let's say you like Visual Studio Code. You can do the same thing with Eclipse or any other graphical environment that is able to communicate with GDB and use your cross compiler for that. We're gonna do this here with Visual Studio Code. So how does it work? You should be in the kernel source code where you have the kernel sources and the VM Linux file. Then you just run VS Code from there. Oops, open it in another window. So this is my VS Code. Now I'm gonna add a breakpoint to that function. So I will do the same thing, write the same test here, but inside VS Code. So I added the breakpoint to the same function, GPIO keys, GPIO report event. Now, what you have to do is create a launch file for debugging. So in VS Code, you can do that typing Ctrl-Shift-D. And then you're going to see this to customize run and debug, create a launch.json file. you should be able here to select this option here, GDB LLDB. But it's important to mention, and this is mentioned in the article, but I didn't mention here. For that to work, you're going to need the C and C++ extension from Microsoft. That's the only requirement. So if you have this extension inside VS Code, you should be able to do this. All right, now we have the launch.json file. This is just automation, right? There is no secrets here. So we just want to tell VS Code to run the correct commands with the correct arguments. Everything else will work magically. For the configuration of this file, I'm going to use what I have in my article because it's easier to copy and paste. So this is the configuration. I'm going to paste here. And then let's check this configuration. So this is to remote debug the Linux kernel. We want to use this extension. This is the program that I want to debug. This is very important, right? The VM Linux file. And this is also important to tell the extension that this is the cross debugger, right? The debugger from your cross compiler. This is mine. If you have a different cross compiler, you might want to change, right, the prefix of the compiler. And here we have the commands to start the debugging. So I'm asking first to load the VM Linux file and then connect into the device. So here we probably need to change because we are using this proxy, right? So here should be this one. Oops. All right. So that should be enough. Before you hit debug, it's important to check and make sure the kernel is in debug mode, or GDB will not be able to connect to the kernel. So for that, you can just echo G, and then now the kernel is in debug mode. Now we should be able to receive the connection from GDB. So now let's just hit debug. It should take a few seconds. It's not as quick or fast as GDB in the command line, but let's say after 10-20 seconds that should work. Just be patient as I'm in now. Now you can see, right, that orange line below, that means it is connected. And we also have here the GDB prompt. That's also very nice. Now you can see like when VS Code starts the debugging process, just runs the kernel, as you can see. So now the kernel is running, but it is connected. So now, since we have a breakpoint, right, that function, that's GPIO keys. So since you have a breakpoint here, and the kernel is running and connect to GDB, as soon as I push the button, it should stop here. Let's try and hope for the best. I pressed the button. It also takes a little bit of time for some reason inside VS Code, but here we go. So now we are debugging the kernel inside VS Code. So now I can, instead of running commands in the GDB command interface, I can just click on buttons, right? So I can just step over is F10, so I can just click here and then step over the code F10 or just type F10. What is nice about a graphical interface is that it's easier to see everything, right? So here in the top you can see all of the values from that from the local variables, right? all of the structures like this bdata structure. You can see everything. In the bottom, you can see the call stack, right? Here, I can just click on the frames, and that's very nice, right? You can even go like into entry.s assembly code. You can step into assembly code, and then you can go like you can really see what happened during that in the interrupt context during this event until it gets into this function. This is very nice, right? So I hope you enjoyed this article. I I will leave all of the links and references and information in the description of the video. If you have any comments, just let me know. If you like this kind of content and want more like this, like just leave suggestions in the comments of the video. And if you really like, just don't forget to click in the like button and subscribe so this video can get to more people. I also have a training on embedded Linux debugging. So if you are interested, I'll also leave the link in the description of the video. And I guess that's it for today. Until next time, bye bye.